Alright, welcome to another AQA A-level chemistry video. Today I'm going to make a video on entropy. I'm not going to be making too much of a big thing about entropy. All I will say is that entropy is quite a big thing in terms of your understanding towards reactions and how reactions happen. Because up until this point, you mostly understand reactions as if the reaction has enough energy, the reaction will happen. Now, there are a couple of exceptions to that rule, and there are a couple of reasons why. Because from what you understand, that all bond forming reactions are exothermic, and all bond breaking reactions are endothermic. But now there's some exceptions to those rules and why they're still allowed to happen. And a big factor of that is to do with entropy. Now, entropy is a measure of disorder. Entropy always increases during a reaction. Entropy or delta H. So enthalpy change is not enough to determine whether or not a reaction happens. For example, when sodium chloride dissolves, the reaction is endothermic. You'd expect the reaction to be exothermic because the sodium and the chloride ion would react with the respected atoms on the polar water molecule. So the sodium ion would react with the partially negative oxygen atom, and the chloride ion would react with the partially positive hydrogen atom, and therefore, because it's bond forming, expect the reaction to be exothermic. But in fact, this reaction is actually endothermic, and I'm not going to go too much into the details of why, but I just want to say this isn't an example of an endothermic reaction where we're actually doing bond forming. Stability. So substances are more stable when they have greater disorder. This means that everything tends to increase its disorder. This is why your phone cables get tangled up in your pocket. It's also why sodium chloride dissolves in water, because its entropy increases. Now I'm going to go through the technical definition of entropy first before going back onto that point there. I should have maybe swapped those around. So entropy, technically, right, is defined as the number of ways molecules can be arranged and the ways of their energy can be arranged between them. Entropy is given the symbol S. A big and positive value of S indicates a large disorder. Now, did I say at the start? Yeah, I said at the start. You don't need to know about the think of this example first. Don't think about the technical definition. Just think of this understanding of entropy first. Entropy is a measure of disorder. Entropy always increases during a reaction. So entropy is just a measure of how disordered your atoms are. The more disordered your atoms or your ions are in a reaction, the more likely they are to react. And that's because if you have a more disordered, I'm going to use this example here, right? So let me get this. The more disordered your atoms or ions are, the more possibilities there are for those atoms to successfully collide and react randomly. The random nature of it isn't actually important. It's just the idea of there's more when those ions are free, they're more disordered, and when they're more disordered like that, there's more possibilities for those atoms to successfully collide and react. Whereas when they're ordered, or when they're not disordered, they're staying in place, and it's less likely chance that there's less different ways in which those atoms or that compound or those ions can react, because they're fixed in that one place. So there's less possibilities, less ways in which that compound can react, less successful collisions per second. The rate of reaction is less. So this would be highly ordered, and therefore the entropy is low, and therefore the chances of these atoms here reacting perfectly in order to form the compound that you want, in this case, dissolving, it would be fully dissolving a chloride and a sodium ions isn't high. So this is not really what you'd want. So this is not really favorable for a reaction. Whereas when you dissociate those ions, and first of all, I want to think about. I'm getting a bit ahead of myself. Sorry. First of all, think about what's actually happening here first. I'll go back to what's actually here. This is This is entropy. If you remember from what I said in my last video, this is the entropy of solution, right? Entropy of solution is the entropy of lattice dissociation plus the entropy of hydration. Now, what we're saying here is that if you want to get the entropy hydration, that's the part we actually care about here in terms of the actually dissolving it, right? The actually part of dissolving it, that's the part that we of which is the hydration. That's the part that we want here. That's the part that I'm talking about. Now you're more likely to dissolve sodium and chloride ions when they've been dissociated. So I'm gonna write actually down here, right? So entropy of entropy of solution is equal to the entropy of lattice dissociation plus the entropy of the sum of entropies of hydration, right? This is the part that this part here is the part that we want. But in order to get, if we want to get this, if we want to have a high probability of this, we increase our chances of gaining the entropy of hydration or having more atoms undergo, more ions undergo entropy of hydration by having the entropy of lattice dissociation. So that's what I mean here, because if we didn't have an entropy of lattice dissociation, it would just mean that our ions would be highly ordered, and therefore the entropy would be very, very low because they're not disordered. They're very, very, we call that state highest state of order is the word that we like to use, highest state of order. And therefore there's less probability, less chances for those atoms or those ions in the sodium chloride crystal lattice to interact with water to undergo the hydration. Whereas when you have the entropy of lattice dissociation and you've dissociated sodium chloride, those ions are more free to move within water because they're separated out. And there's more disorder. They're more disordered. They're less arranged. When I think about disorder, just say it is no special way of saying it. It's literally what it sounds like. How disordered something is, right? So this is more disordered than this. That's what I'm saying. You want, in a reaction, you would want this over this, because this is more, they're more spaced out, they're more disordered, they're more randomly ordered and disordered, and therefore there's more possibilities for these ions to react, and have more in terms of reactive, the successful energy to react, as well as that you have to think about the activation energy as well. They're more likely to successfully collide and react than these, because there's less probabilities because they're so packed orderly together. So you limit the number of probability of chances for them to react. So in essence, the higher the disorder, therefore the higher the entropy, the more likely the reaction is to happen. Now there is an equation that actually links this principle of disorder, of entropy. Disorder and entropy really are the same thing, really. There's an equation that links entropy, temperature, entropy change, and something we call Gibbs free energy. And also I'm going to talk about that in my next video, but those are that equation, when I talk in, that will be in my next video, actually explains how likely a reaction is to happen. And this is why having a high entropy in itself doesn't necessarily mean the reaction will happen, because it depends on how how that affects the reaction. But usually, if your value, well, you'll see in the next video what I mean by that, but usually having a high entropy usually means that the reaction will happen, but there's a threshold, and you'll see it in the next video when I explain the equation, why having a high entropy doesn't necessarily mean the reaction is feasible, because there might be, if you look at the equation, if you don't reach a certain value, it means the reaction isn't feasible. But I'll go through that. That's something that I will be going through in another video. I just wanted you to understand what I meant by entropy, why it's so important, and why it makes the reaction more likely to happen. Hopefully this made sense. If it still didn't make any sense to you, leave a comment in the video, and I'll try and explain to you as to why. So substances are more stable when they have greater disorder. This means that everything tends to increase its disorder. So most reactions like to increase the disorder because it means they're more stable. The reaction is more stable to have for it to recur. And it's kind of partly the reason why if you look at your phone, when you put your phone in your phone cable in your pocket, not sorry, phone cable, your charger, your, let's say your back in the day if you had wireless earbuds, right? It's not wireless earbuds, wired earbuds, right? If the ones with the strings, I know some people probably don't remember them anymore, but most people remember them, right? Those wired earbuds, or even your phone charger, the wired ones, when you put them in your bag, especially if they're really long cables, they'll tend to tangle up, and that's because of this. It's more stable for them to be like that because there's more disorder. And that's just a little side note I found on Seneca as well. So I thought it'd be quite interesting to mention that. But it's also the more serious note, right? It's also why the sodium chloride dissolves. Oh, it's also why the sodium chloride dissolves in water, even though it's an endothermic reaction, and that's because its entropy is increasing. And as I said before, I'll go through the exact reason in the next video when I actually go through that equation. It's called the Gibbs free energy equation, but as I said before, I'll go through that in that video. Now, the factors affecting entropy. Entropy is affected by many factors, including temperature, physical state, and number of moles. So first I'm going to go through the temperature. So an increase in temperature increases the speed particles move at, i.e. it increases the kinetic energy. I'll put it separately. You know what? I'll put it here. It affects the speed that particles move at, but it's because they have more kinetic energy. Oh, sorry. Now, why I want to emphasize kinetic energy, because saying that this particles, you already know from GCSE that if you increase temperature, particles will move faster. But giving a more A-level explanation saying that it moves faster because the particles have more kinetic energy. So that's just important to say that. He didn't mention it there, so I just thought I'd mention it on the side. But but you already know that, so I'll get back to it. If you increase temperature, particles have more kinetic energy, and therefore they'll move faster, and therefore they will collide more. But what's actually more important is that when they're moving faster, they're more likely to be disordered, and so entropy would increase, right? So, for example, what I mean by this is that if you had, I'm trying to think of an example here, right? Okay, yeah, I can think of an example, right? All right, yeah, sure. Yeah, I can think of it now. So let's say you had like one of those old raffle machines, right? Those old raffle machines. So it's like, if you remember, like if you've seen any of these raffle machines, or you know what, it's even if you had like you had if you had a five balls, right? Let's say I had a hat and I had five balls in a hat, like they do with when they're doing um the UEFA Champions League draw. They don't use a hat, but they use like a little spherical ball thing, right? But let's use a hat because maybe not that many people watch football, right? But let's say you had five balls in a hat. You have a more if you swirl them around slowly. I know this is to do with heat, but heat is technically talking about the kinetic energy here and speed, right? If I was to slowly move my hand in that hat to rearrange those balls, they're gonna be disordered, yes, but that's gonna be much different compared to if I move my hand really fast in that hat, really quickly, and then with the same time, right? So let's say in 10 seconds I'm gonna put my hand in a hat with five balls in it, or let's say 10, right? Let's say it's a big hat so you can fit 10 plastic balls in there, right? And I move my hands quite slowly, and then compared to me moving my hand very, very fast, I'm giving the one that's gonna have more disorder, the one that's gonna have the balls more randomly arranged in that in that hat, or more disorderly arranged, is when I'm doing it faster, because I'm giving those balls more kinetic energy to move around that hat, and therefore I'm doing hand gestures, but I forget you can't see that. But I'm giving those balls more kinetic energy in that hat to move around when I'm moving my hand much faster, because there's an increase in that. As I said before, more increase in that kinetic energy, they can move much faster, and therefore they're more disordered, and therefore you're getting the outcome that you most likely want. Now in this case here, if we're talking about a reaction in a beaker, it's more increasing the temperature increases the entropy, and therefore makes the reaction more feasible, because if you increase the temperature, you're making those atoms more, you're increasing the kinetic energy of the particles move more faster, and therefore they're more disordered. When they're more disordered, there's more possibilities for that atom or that compound to react with the other reactant in order to get your product. Whereas if you have a low temperature, those particles have less kinetic energy, less energy to therefore have less kinetic. If they have less kinetic energy, they'll move less, and therefore they it's still stuck within, it's still pre-ordered. Those atoms are pre-ordered, so the entropy is low, and therefore there's less possibilities for that reactant to react to the other reactant. And I'm not talking about the energy the particles have to react. I'm talking about how many different orientations that, because also the there's two things. If I should have mentioned this, actually should have mentioned this at the very start, right? There's two things that you need for a reaction. One of them is the activation energy. Another thing is called stoichiochemistry. Stoichiochemistry has to do with the arrangement. So the particles actually have to react in a certain way. They can't just react, hit each other randomly. They actually have to collide with each other in the right orientation. But when you have, as I said, now if you think about it, if you had more disorder, a higher entropy, there's more ways that those atoms can, that you open yourself to more ways that those can react. There's more possibilities. Whereas if you close yourself to the edge, it's like the crystal isn't broken down, or it's very minimally broken down. That crystal you have isn't being broken down, and therefore because you have a very low temperature, there's only one particular side of that atom that's exposed in order for it to react with the other reactant. So hopefully you understand what I mean here. So when you're more, you know what, I'll show you what I mean here. I'll show you what I mean here, because I'm getting way too maybe I'm going a little bit over the top here. So let's say this atom here, right? The one I just highlighted here. That green one there. There's only one space or a couple of spaces for that green atom there, which is meant to be the chlorine, right? That one on the top left here. That's a bit thick, but it is what it is. You can see what I mean there. There's only one or couple of spaces for that chlorine atom to react with water. Whereas if it's separated out, so here it's got low entropy, i.e. it's got low it's still very ordered, whereas here it's more disordered. That same chlorine atom is more disordered and it's more free, and it has more possibilities to react with the water in order to go undergo hydration. And that's what I mean here. So when you have low temperature, if I'm bringing it back to the example, I'm not going to use the example of the hat, but we're going to use the example of molecules, right? If there's low temperature, those particles have less energy, less kinetic energy, therefore they move less, and they're still staying in that form of order, and therefore there's low entropy, and there's less possibilities for those atoms to successfully collide and react, or there's less possibilities. Whereas when they're more disordered, there's more possibilities for those atoms to successfully collide and react. Hopefully that made sense. I know I kind of rambled on a little bit too much there, but if you want me to explain again, I can do it in the comments. But I think that made sense. When it's more disorder or more entropy, there's more successful ways. So there's more possibilities for those atoms to successfully collide and react. All right, now I'm going to talk about physical state. So molecules and gases are free to move. so molecules and gases are free to move. This means they have the higher entropy than solids and liquids, and it's the same way with liquids and liquids have a higher entropy than solids. So, if example here, this is an example of a liquid. We know how liquids are, right? So we know that they're still liquids are still they're less densely packed together than solids, but they're still more densely packed together compared to gases. So these here have, because they're less, liquids are more. Let's start with solids, right? Solids like this would have very, very low entropy because those atoms have less space to move around. So therefore liquids, because they have more space to move around, they're considered to have higher entropy than solids, right? They have more high entropy than solids. However, gases are even more free to move than, so let's see this is examples of gases, right? They have all the air, all the space in the air to successfully move around, and therefore, so I say successfully move around, just to move around, sorry, not successfully move around, just to move around, and therefore they have even higher entropy than liquids because they're more free to move around than liquids, and liquids are more free to move around than solids. So solids have the lowest entropy because they can't move around as much. Liquids have a higher entropy than solids, but gases have a more higher entropy than liquids and gases. So number one, highest entropy gas, second highest entropy liquids, third highest entropy solids. Number of moles. So if there are more moles, if you have more moles of a compound, there are more ways you can arrange 10 particles, for example, than 2 particles. So the more moles of a substance, the greater the entropy. So if you're in your reaction, if you're increasing the number of moles, you're increasing the entropy because you're producing more amounts of that particle, more numbers of that particle, and therefore there's more ways those atoms can be those compounds or particles can be rearranged. So whereas if you are, so let's say that in your reactants you had 5 moles of products in total in 5 moles of reactants in total on the reactant side, but when the reaction actually happens, you form 2 moles of product in total. This would be considered this would actually decrease entropy. This was considered to be a less feasible reaction because the entropy is lowered, because there's less ways that those atoms could be rearranged because because obviously you're decreasing the number of atoms, less ways they can be rearranged. If there's less ways you can rearrange them, it's more ordered, and hence if it's more ordered, it's less disordered. So therefore, since we know entropy is a measure of disorder, this reaction would be decreasing entropy because where the atoms are becoming less disordered or they're becoming more ordered. Whereas if I was to flip this round, right? I flipped that round. Actually, no, I just and let's say we're going from 2 moles in reactants to 5 moles in reactants. This would be a highly feasible reaction. Well, it's more likely to be a highly feasible reaction, as I'll explain in the next video. Because we're increasing the number of moles in the reaction, and therefore, if we're increasing the number of moles in reaction, we're increasing entropy. And because there's more, so if we're increasing the number of moles in a reaction, we're increasing the number of particles, and therefore if there's more particles, there's more ways those particles can be disordered, and therefore we're increasing the entropy. Now, I'm not going to go too much, and you don't need to actually know this, just a little fun fact, but I'm not going to go too much in depth. If you wanted to know the number of ways that you could, the number of different possibilities for something to be ordered, the number of different ways it can be ordered, we usually use factorial. It's a maths thing, right? So, if you have two things, right? 2 factorial, just 2 times by 1, there's 2. 3 factorial, 3 times by 2 is 6, right? So if I'm going from 2 moles of our reactants to 3 moles of our end products, right? So if they say it's 2 to 3, I'm going from 2 possible ways I can order those compounds to 6 moles. Take 6 different ways I can order those compounds, or sorry, compounds, reactants, atoms, whatever. But just showing this little thing here, or 4, right? Or let's use 5. Let's use 5 because that's the one we have here. 5 factorial would be 5 times by 4, 20. 20 times by 3, 60. 60 times by 2, 120. If I'm not mistaken, should be 120, right? I'm not dumb. Yeah, it is 120. I don't know why I took so long to say that. I didn't want to sound dumb there, but it is 120. I had to check on my calculator, but I was certain that it was 120. 5 times by 4, 20. 20 times by 3, 60. 60 times by 2, 120. But the point being, right, not for me getting shamed for my terrible maths, right? But the point being, I'm going from 2 possible ways I can. If I'm going from 2 to 5, right, that's a highly entropitous reaction. Entropic reaction, because I'm going from 2 ways I can order my compounds to 120 different ways I can order my my reactants, or my products. 2 ways I can order my reactants to form 120 different possible combinations in order to form my products. And therefore there's much more disorder there, and therefore much more likely that if they're more disordered, higher entropy, and therefore the reaction is much more likely to happen. Conditions of a reaction, right? So these all mean that a reaction is more likely to happen if the reaction increases the number of moles of the substance, the reaction produces gas and consumes solid, and the reaction is exothermic. So all this just means here is, wait 1 second. Yeah, sorry. All this means is that if the reaction is more exothermic, we're increasing the temperature. Increasing the temperature increases disorder, hence increasing the entropy. The reaction produces gas and consumes solid. So the reaction gets rid of gases. So if we're going from, let's say all of our I'll actually use, I haven't got the best example here, but let's just use carbon solid plus gas, and then goes to form CO2 gas, right? So this reaction is highly not highly, but it has some entropy because it's going from solid and a gas to just gases, and therefore this is more favored in terms of the fact that there's we're going from a state of matter that has low entropy to a state of matter that has high entropy. And don't think about although it has going from 2 to 1, that is less entropic because we're forming less moles, but we're going from we are going from one atom which is coming from a low entropy, has a low entropy, one state of matter that has a low entropy, with one that has high entropy, to one that only has high entropy. So if we're getting rid of solids or getting rid of liquids to form gas, or getting rid of solids to get liquids, or getting rid of liquids to form gas, that would be highly that would increase the entropy, because we're going from states of matter that have states of matter that are allow atoms to be more freely arranged, and therefore have increased disorder, and therefore increasing the entropy. And hopefully that makes sense. And the number of moles, already explained that one right already. Entropy calculation. So standard entropies, right? Over time, chemists have developed a table of entropies of hundreds of molecules and elements. These entropies are all measured under standard conditions of 1 atmosphere pressure and 298 Kelvin temperature. To calculate the entropy change, you must find the difference between the standard entropies of the products and the reactants, i.e., all it just means is, if you want to work out the entropy change, or delta S, delta meaning change, we're just doing entropy of the products. And this is something you have to do in your exam when you are asked to work out the entropy change. But it is It just makes sense, right? I said it here. It just makes sense. If you want to work out the entropy change, just do the entropy of the products minus the entropy of the reactants. And that's it. And it'll be very obvious what it is. They'll give you a table, as if they'll give you, chemists have actually developed a table, and in the exam they'll give you the entropy of the specific atoms or the specific compounds that they want you to work out. So don't worry about that. All you need to know is that if you want to work out entropy change, just do products minus the reactants, or entropy of your products minus entropy of the reactants. For example, the Haber process, right? So the equation for the Haber process is here. If the entropy of nitrogen and ammonia gas is, yeah, it's just a quick example here, right? If the entropy of nitrogen and ammonia gas is 192 kilojoules per mole, and the entropy of hydrogen is 131 joules per Kelvin per mole. I didn't say kilojoules per mole. Sorry, the units of entropy, by the way, is joules per Kelvin per mole, right? I actually write. Let me write it here because I can't really do it that well on this. It's joules per Kelvin per mole, and that's because of the way, as if when I show you the equation in the next video, it's very easy to see why this unit is formed. But that's how you guys should know how units get formed anyway. But it's just in the form of energy per temperature per mole, and you can use kilojoules per Kelvin per mole. They do allow that. You can use either or, unless they specifically say they want it in joules per Kelvin per mole, put it in kilojoules per Kelvin per mole. If they want it in kilojoules per Kelvin per mole, put it in kilojoules per Kelvin per mole. But you should know just using it is just a times 1,000. But you should know that kilo is pretty simple, right? But here, if they gave you an example where they wanted you to work out the entropy change of this reaction, and he told you that the entropy of nitrogen and ammonia is 192 joules per Kelvin per mole, and the entropy of hydrogen gas is 131 joules per Kelvin per mole, what is the entropy change? Now, the entropy change would be 2 times by, right, because we're doing products minus the reactant, right? Products minus the reactants. Therefore, it'd be, they said nitrogen and ammonia are both 192, so it'll be 2 by 192, because ammonia, there's 2 moles of ammonia. There's 2 moles of ammonia in our products. So 2 times by 192 minus the reactant side. So the reactant side is just 1 mole of nitrogen, which is just what is it? They said nitrogen is 192, so it's 192 plus 3 times by H2, so 3 times by 131, which is just 393 anyway. So I'm not gonna just, you know what, I'll put this anyway. I'll put it like that. We already know it's 393, but always good to represent how represent it like that. To show them where you got the 393, not just saying 393 out of nowhere. So 2 by 192, right, minus 192 plus 393 minus 201. So here, minus 201 joules per Kelvin per mole. Sorry, there's not really much to say, but you get the point, right? Obviously, in the real thing, don't do it like that. Put it down here where there's more space. All right, so it's minus 201 joules per Kelvin per mole. And this fits in well with the observation that the Haber process doesn't produce much ammonia. Now, this makes perfect sense. It makes perfect sense that this suggests to me that this is not a highly entropic reaction. The entropy for this reaction is low because the entropy is less than 0, which means that this reaction becomes more ordered. That's what this means. It means that this reaction is becoming more ordered. If it's becoming less ordered or highly disordered, right, therefore the entropy would be higher, but it's a negative value, minus 201 joules per Kelvin per mole. And look at it here, we've got 4 moles of gas to form 2 moles of gas. So we're actually decreasing the number of moles, and therefore we're going from 4 moles to 2 moles of gas. So to say a matter say is saying that's not going to be a problem for us, but we're forming 2 moles of gas, and therefore 2 less moles of gas, and therefore there's going to be less different weight. Sorry, I can't say that. 1 second. Sorry about that, my alarm went off. But there's going to be, if you have, if we're decreasing number of moles, there's less possibilities for those, there's less different possible ways that those compounds can react to one another, and therefore we're decreasing the entropy, and therefore this reaction is actually going to be less, it's less likely to be feasible. I have to be very careful with the way I word it, but definitely for certain that we would expect our entropy to be negative here. And that's it. I know this video's been kind of long, but that's it. So just three things that we need to the three things that would affect our reaction is just saying, or that would affect entropy, are temperature, change in moles, change in number of moles, and the way that we change our state of matter. And that's it. Hopefully the video was helpful.